So the pink star, 59 point something carat pink diamond, considered a fancy vivid pink, flawless, sells at auction at Sotheby's 2017 for 83 million US. That's with commission fees, but it's estimated at a value in 2017 of $71.2 million. Holy crap. Okay, so the color and then the stone. Colors of diamonds, that can be typically, like a blue diamond would be affected because there are trace amounts of boron, the element in the lattice structure of the diamond. So the diamond itself formed from carbon that has combined in a certain structure that's called a lattice. It has to do with the angles at which each molecule is at in reference to each other. And it's consistent throughout in a diamond, and it's called a lattice. So in a blue diamond, boron has contaminated this structure, and because every element has unique properties about it, unique signatures, if you will, the number of protons present. One of those properties is also how it emits or absorbs light, or the amount of energy required to move an electron from the shell or the location that it lives in to a different one, a different shell level. Not within that shell, but a totally different level. And there's a certain amount of energy required, and that amount of energy ends up being able to be read in how it emits or absorbs, takes on or gives out light. So pink diamonds are unique though. It's not because of an element present. This is the leading theory because of what they think would have been a massive pressure shift. What they think, again, what's leading is that a great seismic shock or an earthquake would have moved colorless diamonds from very deep within the Earth's surface, very deep to the Earth's surface, and then they would have been pushed much closer to the surface. And that pressure change, combined with the initial shock itself, they believe could have changed how the molecules formed. That's the leading theory on why they're pink. But the diamond part, why diamonds reflect or just look so brilliant and are so captivating, this has to do with two things: refraction and reflection. So refraction is how light behaves in different mediums. In air, and when I say air, I mean like in a vacuum, no outside influences, just pure. Light moves at a certain speed, and that's constant. It is 300 kilometers per second. Now, through different mediums, like water would be a different medium, a diamond is a different medium, it travels at a different speed. Diamonds actually have the slowest speed, the biggest reduction in speed, going from a vacuum into a medium. It's the highest, it's 40% the speed of in a vacuum. This is referred to as the index of refraction. And it's a number, it's a constant for a certain material, and you get that constant, which is referred to as N. You get that constant by taking the speed of light in a vacuum, 300 kilometers per second, and you divide it by what the speed of light is through whatever medium, in this case diamonds. And at 40%, the speed is 124,000 kilometers per second. So when you divide the speed of light through a vacuum by the speed of light through a diamond, the number you get is 2.42. So the index of refraction of a diamond is 2.42. The index refraction through air is considered 1. So it's a pretty big difference. So another way to think of refraction, if you think of the example given in the chapter is a good one for me because I was a lifeguard. So if a lifeguard sees a swimmer in distress on a beach, the straight line being the shortest distance is still not the line that the lifeguard is going to choose. They're going to choose to run at a certain angle along the beach because they can travel faster on land, just like light travels faster through the air. Then they will choose a point at which to enter the water that will create the shortest distance to get to the swimmer. The idea is not to cover the shortest distance, it's to cover the distance in the shortest amount of time. So you change your angle. Light travels through a vacuum at one speed, hits a new medium, and the angle will change. Refraction. Diamonds, that change is so drastic that it refracts and ends up creating a number of different possibilities for where the light can then either exit a stone being reflected back through the top of the stone, or that index of refraction that's so important. This is because what that really starts to do, I need to find the correct term. This starts to, the speed at which the light changes, because the inside of a diamond also has angled sides and surfaces, there is a certain angle that is optimal for the light to either be reflected back outside of the stone, or for the light to actually start to come back up, but then hit the interior surface of that flat surface and bounce the light back inside. That is called total internal reflection. Best way to think about that, if you're in a car, this angle of how lights hit. If you're in a car and you're stationary, you're waiting at a light and somebody pulls up beside you, the light might reflect from the sun off of their mirror at just the right angle that it blinds you. But if you just move a little, you're fine. That's because that perfect reflection of light only happens at a very specific angle. Otherwise, it gets lost. The light's still there, but it's not perfect. That total internal reflection is what we're going for. There'll be an angle at which the light ends up hitting that internal surface and bounces back. When the bouncing continues to happen, you get that brilliance where light just seems to be coming from within it. It's not producing the light, it's just using the refraction to reflect it perfectly. I'm done.